So in the today's class, we are starting with the law called as Complementary Law. The name of the law is Complementary Law. The Complementary Law states that when a variable is ANDed with its complement is equal to 0 and a variable is ORed with its complement is equal to 1. So it means this law states that when you take a variable and perform the logical multiplication of its complement, then the result is 0. This is one case, according to the law. Then second one, take the variable and perform the logical addition with its complemented variable, then the result is equal to 1. That we are studying it as like this. The complementary law states that when a variable is ANDed with its complement is equal to 0 and a variable is ORed with its complement is equal to 1. It means we are taking the same variable, then one normal variable and its complemented form, that is complement of the same variable. Suppose x is a variable, then take the x complement. Once you can perform logical multiplication, you get the result as 0. Then take x and its complement, x complement, perform the logical addition operation, then the result will get it as 1. This is the statement of complementary law. So based on this, we have the theorems. That is theorem number 7. X plus, this is x complement, it is x plus x complement, right? So x plus x complement is equal to 1. So x plus x complement equal to 1, right? So this is the meaning of that particular statement. Take the variable and its complement, perform logical multiplication and logical addition operation, then you can check out whether you get it or not, right? So x plus x complement is equal to 1. It means we are starting with the first one now. If x plus x complement equal to 1, then you can take as usual that LHS, right? So x plus x complement equal to 1, take the LHS and check out that. Proof, if x equal to 0, then take the LHS. LHS equal to x plus x complement, that is equal to 0 plus 0 complement. Zero plus 0 complement. The next step you can write it as, here something it is, mistake is done here. So I can write it as 0 plus, the 0 complement is 1. This 0 complement becomes 1. So according to the OR relation, 0 plus 1 equal to 1. 0 plus 1 equal to 1 you can write, then that is nothing but RHS. I hope it is clear to you all. Some mistake is there here. Instead of 0, you'll write it as 1 this one, because this is 0 complement. 0 complement 1's next step what you'll get is 0 plus 0 complement is 1. So 0 plus 1 is 1, that is equal to RHS. This is the first case. And in the second case, if you take x equal to 1, then LHS equal to x plus x complement. X plus x complement. So next step what you can do is, x value is 1, so plus x complement is there, so x value is 1, 1's complement, that is in the next step you can write it as 1 plus 1's complement is 0, so 1 plus 0 is according to OR relation, that is again 1, that is equal to RHS, hence the theorem is proved, that complementary theorem, x plus x complement equal to 1. Then In this, according to the question you have to answer, that is, if it is algebraic, you can write this one, or else if it is a truth table, you know, already you have practiced a lot. 6 times you have practiced a truth table. Here also, we have the same method. You can write or you can prove this particular theorem by using truth table also. Then I'll move on to theorem number 8. That is x dot x complement. When I'll get this bold letter, that is a complement I use in the notes. So x dot x complement is equal to 0 by complementary law statement. So again, you have to prove it. First case, if x equal to 0, then take the LHS, x dot x complement. X dot x complement. You can substitute the value of x as 0. So next step, 0 dot 0 complement. 0 dot 0 complement. So the next step, you can write it as one more step if you want. That is 0 dot 0 complement is 1. So we know the AND relation, that account to AND relation, 0 dot 1 is nothing but 0, that is equal to RHS. Then second case, take x equal to 1. If x equal to 1, then LHS equal to x dot x complement. So substitute the value of x as 1. So 1 dot 1 complement. That is equal to 1 dot 1 complement is 0. So you can write this 1 to 0. That is 0 means that is equal to RHS. So hence the theorem is proved. This is called as complementary law. In complementary law, we have two theorems. That is theorem number 7 and theorem number 8. When a variable, right, the statement, when a variable, what you learned that? Is ANDed with its complement, that is a product, is equal to 0, and a variable is odd with its complement equal to 1. So this statement we have proved by taking theorem number 7 and theorem number 8. Then next theorem. Before that, again we have to study one definition in the form of one law, that is called as Involution Law. Involution Law. What the Involution Law states? The Involution Law states that when a variable is inverted twice, when a variable is inverted twice, not once or once, it is inverted twice, is equal to original variable. One variable na ಎರಡು ಸಲ ನೀವು ಕಾಂಪ್ಲಿಮೆಂಟ್ ಮಾಡಿದ್ರಿಂದ ಡಬಲ್ ಕಾಂಪ್ಲಿಮೆಂಟ್ ಮಾಡಿದಾಗ ಅಗೇನ್ ನಮಗೆ ಸೇಮ್ ವೇರಿಯೇಬಲ್ ಸಿಗತ್ತೆ ಅಂತ. This is the meaning of involution law. The involution law states that when a variable is inverted, it means complemented twice, double complement, you will get it as the same variable. So according to this, we have one theorem, that is x, right? So for x, I'll choose here again so x double complement, say x double complement, x double complement equal to x. X double complement equal to x. What is this? This is according to involution law. This law states that the variable is inverted twice. I have complemented twice this variable. Then the result is again the same variable. X double complement equal to x you will get. So this means, first you can take the proof in the proof case. If x equal to 0, then what about x complement? X complement becomes 1. If x equal to 0, x complement equal to 1. Take again the complement of this, right? Then x double complement or x double complement equal to 0. I taken x equal to 0. I found the complement of that is x complement equal to 1. If I again complement this, that is called as x double complement to 1 becomes 0. Normal variable x equal to 0, its complement is 1, and you perform again its complement, you will get it as 0. It means I taken x equal to 0, again in the result I am getting it as 0. According to involution law. When a variable is inverted twice, again you will get the same variable. This is first case. Second case also. If x equal to 1, then x complement equal to 0 you will get. Then again if you complement this 0, x double complement equal to, you will get it as 1. X double complement equal to 1. It means I have taken x equal to 1. The result of what I am getting after double complement is again 1. That's why the law stated that when a variable is complemented or inverted twice is equal to the original variable. This is also exam point of view for 2 marks econ theorem. Then next we'll go. The next law again. The next law is called as commutative law. So commutative law. So this law is already known to you all because in the high school level you have studied this, that commutative law for addition and commutative law for multiplication, both you have studied that. So based on that knowledge, again you can prove it here. The commutative law states that the order in which two variables are OR means logical addition, or athava ANDed means logical multiplication, makes no difference. If you take the variables and change their order and write it with the logical addition or with the logical multiplication, will not get any difference. That is the statement of commutative law. The commutative law states that the order in which two variables are OR or ANDed make no difference. So based on this statement, we have theorem number 10 and theorem number 11. First we'll prove there is theorem number 10. So first we'll go with OR operation. That is, theorem 10 states that x plus y equal to y plus x. There are two variables x and y. If you write this in different orders, then also with the OR operation, this will not make any difference. X plus y is equal to y plus x. The result will be same. That we are going to prove it now. Again, by proof by perfect induction method only. First, that is algebraic method. Proof: if x equal to 0, then LHS equal to x plus y. Substitute the value of x as 0. So substitute x as 0 here. So 0 plus y, keep it as it is. So that is equal to 0 plus y is nothing but y by theorem. By theorem, 0 plus y is nothing but y. Just like what you learned in the previous theorem, that is 0 plus 1 is nothing but 1. Based on that theorem, you can say that 0 plus y equal to y. So when x equal to 0, we took LHS, then the output order rating is y. Now, take RHS also. The theorem proof is now changing here. Up to 9 theorems, the method was same. Even 8 theorems, the method was same. But from 9th is changed, even 10th is going to change now. Again, take RHS also. Up to 8 theorems, we have taken only LHS and proved. But this theorem onwards, I told in the beginning that some theorems can be proved in different ways. Right? The method changes. So here I'm going to change that. Take the RHS and check it. So RH is equal to y plus x. Again, substitute the x as 0 for this also. Keep y as it is, plus x value is 0. So y plus 0 is equal to y by theorem that we have learned already, that is 1 plus 0 is equal to 1 you have learned. Based on that, you can write it as y plus 0 equal to y. For x equal to 0, what we are getting is LHS equal to y we got, then RHS we took, for that also y we got, it means LHS equal to RHS. So this is case 1. In the same way, we can take that if x equal to 1, then take the LHS, x plus y. LHS is equal to x plus y. Substitute the value of x as 1. So that is equal to x value is 1, so 1 plus y. So 1 plus y is nothing but 1. By theorem again, 1 plus y is equal to 1. Take RHS and check out now. So RH is equal to y plus x. So substitute the value of x as 1. So y plus 1, that is equal to 1. So to check it here, the LHS is 1, even RH is also getting it as 1. It means LHS equal to RHS. Theorem is proved algebraically. So this is first method. Even this theorem we are going to prove with the help of truth table. Now you can check out. If you check the theorem, x plus y equal to y plus x. Here, how many number of variables? The number of variables are 2. 2 number of variables. If the number of variables are 2, then substitute the number of variables 2 in the general form, that is 2 power n, where n equal to now 2. So that becomes 2 square. 2 square means that can be expanded as 2 into 2. That is equal to 4. That 4 is nothing but, to prove this theorem by using truth table, we need 4 rows. Then after knowing these 4 rows, you can draw the truth table with 4 rows and 1 row as a heading. Then now you can learn this, how to write the column headings. So we have started observing the theorem. The first term is x. For that, one column is prepared. We are given for first column, we are writing it as x column. Then second term is y. For that, we are writing it as a second column is y. The RHS, if you observe, again same things are there, but different order. So we are not worrying about that. So now you can check complete LHS. That is x plus y as a third column. Then in the RHS, we have x and y both, only order is changed, that's why directly no need to write y column and x column, or if they are there here in the form of x and y, so directly you can write it as y plus x as the fourth column here. This is the way you have to write the column headings. Once columns are ready, now you can write the different combination of values for the variable x and y. There are 2 variables. We need 4 rows. It means 4 different combinations of values we have. First case, we are considering that when x equal to 0 and y equal to 0. First case. And second case, when x equal to 0 and y equal to 1. And in the third case, we are reversing that x is 1, y is 0. And in the last case, we are taking that x equal to 1 and y equal to 1. Both are 1, 1. So 0, 0, 0, 1. 1, 0, 1, 1. These are nothing but binary numbers in 2 bits, 0, 1, 2, 3. Once you have completed these inputs, then perform the required operation. Depends on the column headings. Now the third column is x plus y is there. So perform the OR operation here, logical OR operation. So 0 plus 0, that is equal to 0. 0 plus 0 equal to 0 by OR relation. Then second row, 0 plus 1. X plus y means x value is 0, y value is 1. So 0 plus 1 is, by our relation again, 1. The same way, 1 plus 0 is nothing but 1. X is 1, y is 0. So 1 plus 0 is 1. The last row, both are 1, 1. That is 1 plus 1 equal to 1. This all we are done by using the OR relation. Again, in the last column also, we are using the complete OR relation, but the only order is changed here. Instead of x plus y, this column is y plus x. Now take the value of y first, then combine that with the x value. That is 0 plus 0 is 0. First value. Then y, second row, that is 1 plus 0. 1 plus 0 is 1. And a third row, 0 plus 1 equal to 1. And in the last row, 1 plus 1. 1 plus 1 equal to 1 by OR relation. So now you can check out LHS and RHS two columns, this third column and fourth column, right? So 0, 1, 1, 1. These are the values in the LHS. Check out the RHS. 0, 1, 1, 1. Both the columns are same. So LHS equal to RHS, and the theorem is proved. Right? So this is the way to prove the theorems. Then one more is that also will complete according to complementary law. That is theorem number 11. Right? So theorem number 11, according to complementary law, for multiplication it is, that is and operation, that is x dot y equal to y dot x. X dot y equal to y dot x. X ANDed with y is equal to y ANDed with x. So again, take in the proof side, first case, if x equal to 0, then take LHS. LHS equal to x dot y. So if the value of x as 0, so that is equal to 0 dot y. So we know that 0 dot anything is nothing but 0. Based on that, even we have studied as an AND relation also, 0 dot 1 equal to 0. So based on that, you can write it as 0. So LHS we got 0. Now take the RHS. RHS equal to y dot x. So fill the value of x as 0 in the next step, that is equal to y dot 0. So y dot 0 according to AND relation again, we get it as 0. That means first case LHS equal to RHS, that is 0 equal to 0 we got. This 0 is there and one more 0 is here. LHS is 0, RHS is 0. So LHS equal to RHS when x equal to 0. The same way you can take it as if x equal to 1, then LHS equal to x dot y. So substitute the value of x as 1, so that is equal to 1 dot y. So that is nothing but 1 dot y is nothing but y. 1 dot y is nothing but y by AND relation again. So now take the RHS and check out. So y dot x. Y dot x. Now substitute the value of x as 1. So y dot 1, that is nothing but again what we'll get is y only. So y dot 1 is y. You can make it this as not 1, this is y. So in both the cases, here in 1, when x equal to 1, we got LHS equal to y and RHS equal to y. Hence, the theorem is proved algebraically. Now you can take the truth table method. So in the truth table method, if you're observing here, the theorem contains two variables. It means again 2 square. 2 square means 4 rows are required. That we have drawn it here, right? So according to that, if you observe here, again, the inputs are same for two variables 0, 0, 0, 1, 1, 0, 1, 1. These are common for all the two variables. What we'll write binary numbers in 2 bits 0 to 0, 1 and 2. 0, 1, 2, 3. Up to 3 we have written here. So again, perform now the AND operation for third column x dot y. That is both are 0, 0. 0 dot 0 is 0. In the next row 0 dot 1. 0 dot 1 is again by AND relation, that is also 0. And third row 1 dot 0 again by AND relation, this is also 0. And last row, that is 1 dot 1 is equal to 1 by AND relation. In the same way, the last column, take y value as first and x value as second and perform the logical multiplication. Again, check the result. So 0 dot 0 is nothing but 0. So first one, then second one, 1 dot 0 is nothing but 0. second one, third one. 0.1 is nothing but 0, and last one, 1.1 is nothing but 1. If you observe the column, third column and fourth column value, that is LHS column and RHS column values 0, 0, 0, 1 and 0, 0, 0, 1, both the columns are same, that is LHS equal to RHS, hence the theorem is proved. So this is about the complementary law for addition and that multiplication.